Thank you, Dr. Hiller, for the introduction, and thank you for proposing the idea of the topic. I didn't know you had presented it 10 years ago. Otherwise, I would have borrowed your version. Well, I got interested in the topic because I think it's something current and I think scientifically proven, and that is affecting the world as a whole. So, just for a head count, who believes in climate change and who doesn't? We all believe in climate change here? Except Mish. Mish said that actually we shouldn't even use those two words, climate change, so I was surprised. I'm really sorry. So, the topics we're gonna, or how I structure the lecture is introduction first, climate change impact in human health, research and historical links, and prediction and prevention. So first, from our president, with all respect, I don't have an opinion on this. The concept of global warming was created by and for the Chinese in order to make US manufacturing non-competitive. So that's a concept. This is another concept from Stephen Colbert. Global warming isn't real because I was cold today. Also, great news, world hunger is over because I just ate. So I thought that was interesting as a reply to our president. This is proof, through research, proof of global warming, how things have changed. I'm sorry Dr. Tony is not here. I was gonna ask him if that's part of his research as well. So climate change refers to long-term statistical shifts of the weather, including changes in the average weather condition or in the distribution of weather conditions around the average. That's just an introduction and a definition. So 10 signs of a warming world. There are some here: Arctic sea ice, ocean heat content increasing, Arctic sea ice decreasing, of course, sea surface temperature increasing, global sea level increasing, and many others that we're going to talk about. Here, more of the facts. The global average surface temperature has increased about a degree in the 20th century. Some people say, some research says 1.5, some say 0.75. The global sea level has increased 2 millimeters since 1961. The Arctic Sea has shrunk 2.7% per decade. And the prediction is that temperature is going to increase from anywhere from 1.5 to 5.8 degrees Celsius in the 21st century, which is interesting. Increase in sea temperature, of course, earth temperature and humidity are part of it. So this is Arctic ice. This is in 1984, about 30 years ago. This is now big difference in Arctic ice and how it has shrunk. This is one of the glaciers in Argentina. This is in 1928, full of ice. Now it's full of water, as you can see. This is another. This is a sequence of the same. This is flooding as part of weather changes. And this is desert now. That actually was before sea or lagoon where boats used to actually transit through. But now it's done. So for centuries, humans have lived in junction with infectious agents, and of course have known about climatic conditions and changes. Romans, for example, used to go during the summer to resorts in the hills of Rome or Italy because they knew about malaria, or at least an agent that would cause some type of disease during that season. In 1878, for example, in the US, El Nino, this oscillation and change in temperature of the wind through the ocean, through the sea, that comes back, usually in the summer, goes to Australia, but when El Nino is around, it comes back with hot temperatures. So we had, in the US, we had more yellow fever, actually at that point in 1878. So part of this has also been created by humans, and there are three transitional periods. One, when Homo sapiens started living and killing and dealing with animals, and then we started having some infections, swapping infections in the era of the Silk Road, for example, from China, passing through India, passing through the Middle East to Europe, with commerce and the military as well. And of course, now, more transoceanic flights. This is a map from the 3 or 4 countries that had more Ebola, and 35 direct flights from there. You can see USA, Europe, other parts of Africa, Asia were involved as well, as we know. So is this the 4th one? Is this climate change era the 4th great transitional period? And is it worsening, or is it just part of the progression that we've seen through history? Of course, to spread and increase the ability of various infectious diseases, we have several things: demographics, environmental, technological, human ecology. Everything plays a role. Part of it is climate change, more of the environmental changes, and it creates a wide range of infectious diseases and an impact in human health. That is what we're going to talk about. So climate health has a primary environmental and social impact, particularly in ecosystem damage, and that is going to create a change in microbial ecology, and that will create infectious disease risk. Also, with these climate changes and floodings and surface water being altered and glacier loss, then we're going to have problems in society as well, like availability of food, availability of water, poor nutrition that will also create a risk for infection, and obviously direct health impacts. When we have this type of natural disaster and events, there is also direct injury and death in the population, which will bring more infectious disease risks. Of course, war is part of it as well. Now, more specifically, climate change through different things like temperature, precipitation, and humidity, wind and dust, will also create an impact in 3 important things: host, pathogen, and transmission cycle. That will increase or decrease infectious diseases through mainly vector-borne diseases, through vectors, or through other vehicles like water or food. So all of these will impact society, and society will have to adapt for it. Now, we have a disease classification based on transmission first, direct, person to person, indirect through a vector or a vehicle, and based on reservoir. Anthropognosis is person, zoonosis is animals, of course. So direct person to person or anthropognosis is physical contact or droplet, for example, less influence of climate per se, and is more influenced by human behaviors like crowding, inadequate sanitation. Some of the examples are measles, TB, HIV. At some point they started as zoonosis, but now are more anthropognosis. Zoonosis is direct animal to animal. It's more influenced by environment, but it's not the one that is more susceptible to environment. And those are hantavirus or rabies, for example. Now, the more susceptible to ecological changes are through vectors or vehicles like water or food. And why is it more susceptible? It's usually because there are more components and more susceptible components like a vector or like pathogen. Malaria, dengue, cholera are part of it. And another indirect transmitted or other indirect transmitted diseases that are zoonosis and that affect humans accidentally are also very susceptible because of the same reason. They have pathogens, they have vectors and animal reservoirs. And we have West Nile virus, Zika, Salmonella, or anthrax, for example. Here is a scheme of the same explanation. And then these diseases are going to be affected by climate, of course. And the transmission components per se will be more affected. The pathogen, the non-human host, the vectors. This is an interesting picture I found. It's a phrase from a British writer: facts do not cease to exist because they are ignored. So just because we ignore climate change or we don't want to see it, doesn't mean that it's not there. As I said, what we're going to talk about more is climate sensitivities and what affects these pathogens, vectors, and infectious agents more. Temperature and fluid level are probably the ones that affect them more, but there are other ones like precipitation, humidity, sea level, of course, wind, sunlight. Even sunlight affects the pathogens and the vectors. So when we talk about sensitivities, we're gonna divide it in vector-borne diseases affected by sensitivities and water-borne diseases. And vector-borne diseases are more temperature sensitivity, precipitation sensitivity, and so on. So to prove this through research, you have to prove a link. And you also have to consider non-climatic factors because you cannot just blame it on climate. You have to prove that there are other things that don't affect it or affect it as well, and you have to do it long term. It cannot just be based on one summer. It has to be based on decades. So when we talked about vector-borne diseases, we see properties in the transmission, and we talk about survival of the vector, reproduction rate, time of the year and level of vector activity, so how much do they bite, and rate of development and reproduction of the pathogen within the vector as well. So first, temperature sensitivity for vectors. Survival increases or decreases, of course. We're going to see changes in susceptibility to some pathogens depending on the temperature, the fluid level, but mainly the temperature in this case. The rate of vector population growth, how much do they grow during that season or during that change. And then changes in feeding rate, host contact, and seasonality of populations, how the populations change depending on those changes. So a question for you. This is a freshwater snail that usually increases when there is an increase in temperature, they tend to extend their geographic area. This has happened in China. These freshwater snails transmit something, and it's right here. You know what it is? You know what this one is? Little egg with a very little spike, if any. Schistosoma. So that's Schistosoma japonicum that was increased in China after a hot summer through these freshwater snails. A couple more questions. Yellow fever and dengue are transmitted by this. The vector is this mosquito host. So which one is that one? Aedes. And actually the larva of Aedes dies when the water temperature is more than 34 degrees, for example. And also the adult dies when the air temperature is more than 40 degrees. So when you reach those points, you're going to have less yellow fever and dengue. Even though we think that usually in a hot summer you're going to have them, if it's too hot, then they will die. What do we have here? This one, when it actually above 16 degrees Celsius, you're going to have more of these. This is going to increase more. What is this first? Malaria. So that's malaria, and of course that one is Anopheles, right? What happens in precipitation and vectors? So usually rain will increase the larval habitat and vector population. Also excess rain, like much heavy rain, can eliminate these vectors because it's going to clean everything and wash it out. Low rainfall, a balance of it. Low rainfall can create habitat by causing rivers to dry into pools. So remember, smaller natural pools will be also a reservoir for these vectors. Decreased rainfall can increase also container breeding because you use buckets to get water. And also increasing precipitation will increase humidity, which increases the vector survival. And the opposite happens as well. Decreased humidity will decrease the vector survival as well. So we have Anopheles here, for example, which will increase survival and population with small natural ponds. Deserts one. Culex, on the other hand, will increase survival when there is drought and dirt accumulates in one location. Rain usually transports and disseminates the dirt, so Culex will not grow there. Humidity sensitivity affecting insect vectors, for example. Important, low humidity and high temperature will limit actually the spread of ticks and fleas. Malaria will also be limited by less humidity, less than 60%. In dry spells, West Nile virus and Lyme will actually migrate to other places, like it has been seen in Canada or Scandinavia. And low humidity also affects Aedes aegypti, decreasing the amount of dengue. Temperature sensitivity now for pathogens will also decrease the incubation period. So when temperature increases, the incubation period of some of these pathogens in the vectors decreases, and it's more frequent, the reproduction of the pathogen as well. There are changes in transmission and changes in distribution. So Japanese encephalitis, for example, requires a minimum of 25 degrees Celsius to actually transmit. But the mosquito that acts as a vector of Japanese encephalitis develops at a maximum of 23 degrees. So that's important when you see the cycle of the pathogen and the transmission. Plasmodium falciparum reduces incubation, and I thought that was very interesting. When the temperature goes from 20 degrees Celsius to 25, the incubation days decrease from 26 to 13 only, about 2-week decrease. Vibrio cholera, and other vibrios, increased growth rate during hot summers. Salmonella increases reproduction depending on the temperature, but when warmer, it increases reproduction. And then Campylobacter concentrates more in surface water at lower temperatures, not at high, but at colder temperatures. Precipitation effects on pathogens. There are not many that are known, but probably the best known is with malaria, the development of the Anopheles mosquito, but more effects on actually vertebrate host. Increased rain can increase vegetation and more hosts, more population, and increased rain will decrease this. Rainy season will actually increase the fecal pathogens. So when there is more rain, we'll stir up the water, and that will increase the distribution of fecal pathogens. So that's important to consider. Humidity will affect also the pathogens. Low humidity and cold temperature will favor influenza, as you can deduct, and higher temperature and high humidity increase the propagation of dengue. At least that was seen in Singapore, with an increase in cases of dengue hemorrhagic fever. Sea level sensitivity is one of them as well. Wind sensitivity will decrease the survival of mosquitoes. More wind, they will die, they cannot fly. Sunshine sensitivity, more sunshine or longer hours of sunshine during the day will increase the survival of cholera. So that's interesting as well. Water-borne diseases, we have all types of water, recreational, contaminated, food water, coastal water. Rainfall will affect the transport of these organisms in water, and temperature will affect the growth, increasing survival of some of these organisms. Some examples: in shellfish, foodborne agents in water, shellfish, Vibrio, for example, will increase in recreational waters in wound infections. Viruses, like enteric viruses, like hepatitis A, for example, will also increase in groundwater and shellfish with increasing temperature. So I thought that this was funny too, part of the global warming. Leonardo DiCaprio trying to find Rose after the Titanic, but it had already melted. So research and historical links. Documented and predicted climate-infectious disease links. There are 3 categories of research. One is short-term variabilities and infections. One is long-term trends and infections prevalence. And then the third one is evidence of links to create predictive models. So these are several research projects that have been done after some natural events like El Niño in 1999, some outbreaks in Venezuela, in Tanzania, during droughts and water-borne diseases and vector-borne diseases. There is a lot of research done, but there is a lot more to do. Some historical links are, for example, St. Louis encephalitis virus, the transmission cycle, where the human is just an accidental host. And we found here in South Florida, actually, not University of South Florida, but in the south of Florida, that each episode of transmission to the humans was from a wet period followed by a drought. So in the spring drought, Culex converges with wild birds, which is a usual host, in a restrictive habitat because there's not a lot of precipitation and rain. And then when water comes back, they start reproducing more and go and bite more humans. So that happened at some point here in Florida. West Nile virus is similar. It was seen in the mid-Atlantic in the US in 1999. And then they saw that warm winters followed by hot, dry summers increased the amplification of Culex as well. And then there were more cases of West Nile. Historical evidence, probably malaria is the one that has had more research and is probably the most sensitive to long-term climate change. So there are some associations like maximum temperature, monthly maximum temperature actually increases malaria transmission. That was in Kakamega. Soil moisture and vector breeding habitats post-precipitations will increase the inoculation and biting of Anopheles as well. Those are some examples only of malaria. And this is kind of how they divide the malaria map in India. And they give it to tourists sometimes to see where there are more cases and where they should be more careful or not go if they decide not to. Then we have El Nino, for example. And it actually happened in Peru in 1997, 1998. They saw that El Nino increased diarrheal diseases in kids more than anything. About an 8% increase in admissions for each degree that temperature increased through El Nino. So there were like about 6,200 more cases that summer. And then other waterborne diseases in the US were related to heavy precipitation months. This is actually how El Nino happened. So the warm water pool should go towards the west. During El Nino year, it comes back to South American and Central American coasts, and it causes flooding. So you have this. This is actually from this year. Unfortunately, Peru went through this again this year. And this is actually an impressive picture of a woman that was dragged through with the river and was trying to come out because she fortunately survived, but it's not a nice experience. So prediction and prevention, environmental influences. There are land use influences, and humans have a lot to do. For example, dams, canals, irrigation will increase the snail host habitat and increase schistosomiasis, for example, or will increase breeding sites for mosquitoes and increase malaria. Urbanization, urban crowding will decrease sanitation and will increase cholera, will increase dengue as well, unfortunately. So there are several examples of what humans have done that will increase problems with climate and some of these pathogens. Other sociodemographic influences that we should work on: human travel, trade, migration, disease control efforts, resistance, and nutrition to help when these natural events happen. In regards to the health sector, there are many things we can do. Carry out campaigns to actually communicate this to people, to prevent some things from happening, some diseases from happening after these floodings, after these natural events, and also to provide adequate healthcare facilities and services, and communication to the citizens of your area is very important, more when this happens. There are predictive models and resources through research, statistical models, mathematical models, all of these to prevent and to create early warning signs and systems for people. For example, the Highland Malaria Project that is examining why now in Africa, instead of staying at a low level, a mosquito was thought to not breed in the highland, but now with the climate change and increased temperature in the highland, the mosquito is actually reaching those areas as well. A good source, a good resource for more information is the WHO Atlas of Health and Climate. Has a lot of information on malaria, dengue, now Zika as well. And I think that that's, those are my references, and I think that that's basically it. This is a picture of Pitbull's, one of Pitbull's albums that is called Climate Change. So if you have heard of it, it has something to do with science as well. Pitbull is putting a grain of salt. So if you have any questions, I'm willing to take them as well. Thank you.